Okay, on our net force versus position graph, we ask exactly the same questions that we ask for the kinetic energy versus position graphs. It's going to turn out that both of our answers to those questions are going to be significant, physically significant. Okay, so first for the slope. What's the slope mean? Slope means rise divided by run. What's the rise of a graph between 2 points of a graph of net force versus position? It's the change in your net force. In this case, that change would be negative. I don't have arrows on this, but you see from the direction of this curve, if we go from this point to this point, the net force is decreasing. So if you're going from here to here, you would have a negative change in net force and a positive change in position. So the rise is your change in net force. In any case, the run is your change in position. So the slope is rise divided by run, which is then represents change in net force divided by change in position. Again, I posed the question, where have you seen a graph of net force versus position? And it took a minute. People thought about it in the lab. Just within the last couple of weeks, we did that for a rubber band, net force versus length of the rubber band, which was net force versus the position of one end of the rubber band. And what was the meaning of that? What did that graph look like? Well, we found that the graph was pretty well represented by a straight line. It wasn't perfect, and it's because of the elastic properties of the rubber band and the polymers and stuff that I don't understand very well, but I can kind of fake it. The slope of that graph was your force constant. Where's the force constant important? Well, the force constant is what you need in order to begin analyzing the simple harmonic motion of something suspended from that rubber band. At first approximation, that slope is fairly close to constant. Okay? So, the slope then would be your force constant if the slope is constant. And your force constant, you can still approximate your results based on a force constant, based on a straight line that does a good job of fitting the graph. Okay, so anyhow, the slope of a net force versus position graph, very important. Okay? Now, if we do the same thing here that we did here, well, it's clear that this is your initial net force, this is your final net force, and that your average net force is going to be represented by a line segment from the x-axis up to the midpoint of this segment, of the slope segment, let's call it. And if we multiply that average net force by the delta x, by the width, just as we did up here, we're going to get the area of the trapezoid. And that area is going to be average net force times your change in position. And what's that? Well, by darn, that's the work done by your net force. And what's that? That's the change in your kinetic energy. Now, where have you seen the change in the kinetic energy? Well, the area between these 2 points on a graph of the net force versus position is the rise of this graph. It's the change in the kinetic energy. So that, to just take us one step further, the integral of this function between 2 points, the integral of your net force versus position graph, is going to be the rise of your kinetic energy versus position graph between the same 2 values of x. In other words, your kinetic energy is an antiderivative of your net force function with respect to x. These are profound interpretations that come up again and again and again. And I said in class, I said, you know, there are approaching 50,000 applications of these ideas. Now, I made up that number, obviously. I don't know how many there are. I don't know how many are valid. Some are borderline valid. But there are many, many applications, and as engineers, you're going to see those applications. You're going to see a lot of applications of these ideas. If you think it's different every time you see it, it's going to be a lot harder for you to learn the engineering. It's going to be a lot harder for you to understand the systems. It's just variations on this theme. You always ask the same question. Whenever you see a graph, these are the questions you ask. Okay? Now they might or might not be important. In this case, this question didn't give us an important answer on this graph, but in this graph it did. In some cases, the question's not going to give you a very important, meaningful answer no matter what, because your graph isn't of something that represents anything that's physically important. Okay? But anytime you see a graph, you need to ask yourself, what does the rise mean? What does the run mean? What therefore does the slope mean? Okay? And then, what does the average graph altitude between the points, the average values of this function, what's that mean? What's it mean to multiply that by the corresponding width, by the change in your independent variable? You get a pretty clear answer if you start thinking about these things, and that answer and that process of analysis and asking yourself questions will pay you dividends every week of your life for the rest of your life, if you're in a field that makes intensive use of the physics or of, it's not confined to physics. You can do the same thing in economics. You do the same thing in just about any field with graphs. Okay, very important to understand this about graphs, and I cannot believe that we're still turning out students who come out of pre-calculus, much less calculus courses, not understanding these interrelationships. You really need to understand them, and you really need to use them forever. Okay, so extremely important ideas.